That's strange. Let's try that again. That's odd. Okay, let's see here. What is going on? Oh. Oh, okay, now it's working. All right, so let's start. So I just wanted to go over some of the more some subtle points about the representations of Su2 and representations of So3. So let me just quickly review what we did so far, and then try to study these objects a little bit more carefully. So so we have this group Su2, and when we want to study its representations, the strategy, maybe I didn't explicitly state the strategy, but this is what the strategy was. So if you have a representation of Su2, what does it mean on a vector space? Let's say what it means is that for every element of the group, we have a matrix. We have an operator on the vector space, and the product of these group elements gives rise to the composition of the matrices, the matrix multiplication. So we're basically trying to represent each group element as a matrix. And in this, this is a list of the irreducible representations. They're indexed by a positive integer, and that integer is the size of the matrix. So in this representation, any element of Su2 is represented as a 2 by 2 matrix. In this one, it's a 3 by 3 matrix, and so on. So what's the strategy for finding these representations? Well, if you have the basic idea, I mean, I'm sure that you covered it in your reading, but the basic idea is that if you are looking for a representation, a map, a matrix, which depends on a group element such that this holds, right? If you are looking for a matrix depending on G, which respects the multiplication of the group, right? Then you can try to differentiate this map at the identity element. That's what we called pi prime. And this pi prime so this pi originally was from Su2, let's say, to UN, a unitary representation. So pi prime would be the derivative, so it would go from the Lie algebra to the Lie algebra. Okay, and the reason we do this is because it's easier to deal with the Lie algebra, because this Lie algebra has has generators x1, x2, x3. It has three basic generators, and we took linear combinations of them to give H, E, and F. This one was the operator which this was the basically the spin operator in the z axis. It was diagonal with eigenvalues -1 and +1. This one was the raising operator, and this was the lowering operator. And so and then the idea was to focus on one of these, namely H, and to view H as defining a circle. So associated to H, there was a U1 subgroup. And that gave us weights, which are drawn here. Okay. And then these were raising and lowering. Okay. Now, I just want to put a little complex numbers here, because part of the strategy was that we should complexify this linear map, because we wanted to make the raising and lowering operators, and that was only possible by taking complex linear combinations. Okay, and this is it. This is the strategy. We're looking for a representation of the group. The derivative of that would be a representation of the Lie algebra. The Lie algebra has a basis. We complexify it and choose a more convenient basis, which is adapted to a particular U1 subgroup. That U1 subgroup has weights. We draw the weights. And because the U1 representations we already classified, and then the E and the F are just moving between the weight spaces. Okay, so when we draw this diagram, the important thing is, here is your positive integer 3. We know that if there is a highest weight vector, one-dimensional space here, then by applying F, we produce a generator for the one weight space, and we apply F another few times, and we get a sum of 4 one-dimensional spaces, each of them an eigenspace of H, but not eigenspaces for E and F. E and F move between them. And that's how we get all the irreducible representations of SU2. So there's a couple of steps, a couple of tricks along the way, and the importance of this complexification is kind of as usual. Whenever you want definitely to have eigenvalues, whenever you want to have eigenvectors and eigenvalues, it's often useful to complexify, and there's no difference here. Okay, so we're gonna study these in detail, and then next week we're going to employ them in the study of the hydrogen atom. Any questions about this? I'm going to go into this in more detail now, but if there's anything kind of high level, ask now. Nothing? Okay, so all right. So I just want to recall the relationship between SU2 and SO3. So SU2 has a group homomorphism to SO3, which is surjective, but not injective, because we have a ±1 subgroup of SU2, which is in the kernel, which is the kernel. So this is here, this is a 2-to-1 covering map, which is very much analogous to having a circle mapping to a circle by theta goes to 2 theta. Okay, it's very similar to that. And this map, we know what it is. It's called the big adjoint action. It's in other words, a group element here inside SU2 will be sent to add G. And this add G, remember what it is? It sends the Lie algebra to itself by taking an element of the Lie algebra and sending it to Gx G inverse. And remember that SU2 is basically the same thing as R3. And so that means that this operator, if you wrote it in terms of matrices, it would be a 3 by 3 matrix. Okay, and remember also that that this X could be written as I W3, or let's say X3 minus X3, X1 minus I X2, and X1 plus I X2. So it could be written in terms of a basis. And this is an obvious identification with R3. Here's X1, X2, and X3, the three coordinates. And remember that the determinant of X is exactly X1 squared plus X2 squared plus X3 squared. So you can see that the fact that this does not affect the determinant of X means that this norm is preserved by this operator, and therefore it lies inside SO3. So that was the abstract reason why SU2 and SO3 are so closely related. But the interesting thing is that if you check what happens with, but note that -1, this is inside SU2. And if we take the adjoint action of minus the identity on X, well, that's just conjugating by -1, and that does nothing. So you see that this is the reason why -1 inside SU2 is sent to the identity element here. Okay, so there are, in other words, -1 and +1 are sent by the adjoint action to the same rotation. And that's the reason why there's a discrepancy between SU2 and SO3. -1 is not the identity in SU2, but when I map it into SO3, it becomes the identity. Okay, so let's say that you wanted to write this map very explicitly. I just want to point out how you would do it, right? You would just have to figure out, you would have to take a general element G. So if G is, let's say, alpha beta minus beta bar, alpha bar, this is a general element. This is where alpha norm squared plus beta norm squared is equal to 1. This is a general element in SU2. And if we write add G, let's say if we wanted to figure out what the matrix, we'd need to figure out what add G of X1 is. It would be some alpha 1, 1, X1 plus alpha 1, 2, X2, sorry, 2, 1, plus alpha 3, 1, X3. And you'd have to figure out X2, X3, right? And you would write out your 3 by 3 matrix. So if we do this, add G X1, X1 is 0, 1, 1, 0. Oh, sorry, I think I'm switching to the Pauli spin matrices. This is self-adjoint, so this is sigma 1. It doesn't matter. I could rescale the basis. It won't make a difference. So if I figure this out, this will be alpha beta minus beta bar alpha bar 0, 1, 1, 0, and then the inverse of this, which is just alpha bar minus beta, beta bar and alpha. And if I work this out, you'll get alpha beta bar plus alpha bar beta, alpha squared minus beta squared, alpha bar squared minus beta bar squared, and then minus alpha beta bar minus alpha bar beta. Okay, and so we can take this and we can express it in terms of the Pauli spin matrices, and so we could write it. We could write this one as 2 times the real part of alpha beta bar times x3 plus the real part of alpha squared minus beta squared times x1. I'm just trying to do this just to emphasize how explicitly you can use these abstract kind of considerations, alpha squared minus beta squared times x2. So I've just expressed it in terms of the other, Pauli matrices, sigma 3, which are, these are just multiples of the xi's from last time. Okay, and so if we write this similarly for sigma 2 and sigma 3, what we get is that add by this alpha beta minus beta bar alpha bar, this as a matrix would be given like this. Notice that it depends quadratically on the entries of the initial matrix, but this is the representation. So I just want to write this thing out just to show you kind of how kind of non-obvious some of these things end up being, even as obvious as even if they start off being quite obvious. And then we have 2 imaginary part alpha beta, 2 real part alpha beta, and alpha norm squared minus beta norm squared. I hope that that's correct. But I just want to point out that, this is just a direct, simple linear algebra consequence of the definition of the adjoint action. Okay, I'm just writing it out explicitly. What happens to a matrix in SU2 when you map it to SO3? You get a 3x3 matrix of real numbers, which acts as a 3-dimensional rotation. And the cool thing about this is that if you multiply 2 of these matrices, and then these will multiply. So matrix multiplication is taken to matrix multiplication. Exactly. And it's kind of not obvious, right? Because these entries depend quadratically on these. Nevertheless, it's still true that if you multiply these two of these together, you'll get the same as this. Okay, now okay, so any questions about this? You could probably see that if you take alpha equals to -1 and beta equals to 0, so if we take the minus the identity element, right, then these are all square of alpha. So alpha is going to be basically, if beta is 0, so none of these terms contribute. We get actually, what is going on? This is an SU2 matrix. I don't like this entry. What's wrong with these entries? Well, to me, it looks like there's some kind of problem. Let me see. What did I write here? I don't know. This sigma 2. This should be here. If someone can see an error, let me know later. These look wrong. This looks wrong to me.
I think the middle entry and the top middle entry need to be switched. At least that way, when you plug in alpha equals 1 and beta equals 0, you get the identity.
Sorry, I don't know what you mean by the middle entry.
Like the 2-2 entry.
This entry.
Yeah. If you plug in alpha equals 1, beta equals 0, that entry should be a 1.
Okay, good. Right, I see now. Yeah, I think I switched the order. Thank you. Okay, great. So you can see if you put alpha equals to 1 and beta equals to 0, only these three will be non-zero and it'll have an identity matrix. Okay, so all right. Now, now there's an important fact that that everyone needs to understand. So I need to explain this very carefully. So imagine that you're studying a representation of SO3. So if you have a let me draw this again. So suppose you have a representation of SO3. Okay, a representation of SO3 would be a map from SO3 into UN. It would, you know, depending on the dimension, it would give a map to some space of unitary matrices. Now, if I have, you know, that's a representation is just a group homomorphism from this small group to this potentially large group. And this is a group homomorphism. So if I have a representation of SO3, I can definitely compose it with this, and I will get a representation of SU2. So any representation of SO3 can be composed with the adjoint action, and this will give a representation of SU2. Okay, but the opposite is not the case. On the other hand, okay, a representation of SU2 does not descend to SO3 unless it has the same value on +1 + 1 and -1 -1. Okay, so remember that this map has a kernel, right? So the, you know, so the alternative, you know, the thing I want you to compare is, suppose that I was given a representation of SU2 into UN. Okay, if this was given, then there is no reason to believe that it would define a map from SO3 to UN, because in order for that to be true, we would need that pi tilde doesn't see the kernel. So it behaves, you know, the image under +1 is the same as the image of it under -1, and therefore, you know, you could say that its value on a certain SO3 element is the following. You could say, take that element, lift it to SU2. There are two possible choices, but it doesn't matter which one you pick, because this representation doesn't care. It has the same value on the two pre-images. Okay, so is that clear? There's a fundamental, what they call an obstruction. So this obstruction is, it's like a test. You know, does pi tilde pass the test of not distinguishing between + or -1? If it does not distinguish, then it passes the test. There is no obstruction, and we get a representation of SO3. Is the concept clear? You should let me know. So the main question about representations, well, okay, so in order, let me phrase it in a slightly nicer way. So to classify irreducible representations of SO3, we may simply look for those irreducible representations of Su2 which descend, which means that they which do not distinguish between between G and minus G inside Su2. In other words, a second time, in other words, pi of G equals pi of G tilde. So if pi of G, so if pi Su2 to Un satisfies pi of G is equal to pi of minus G for all G, which is equivalent, by the way, to pi of minus 1 equals to 1, pi of 1. Okay, then pi is the composition of, let me call this one pi tilde, sorry. If pi tilde is a representation of Su2 satisfying this condition, then pi tilde can be expressed as the composite of add with pi. For pi, a representation of SO3. Okay, this is the basic idea. Okay, so let's do that. So I'm going to implement this. I'm going to make this check. I'm going to check it out. I'm going to figure out, because we have a full classification, I'm going to look at each representation and I'll figure out whether it descends to SO3 or not. Okay, so let's proceed with this. So let n be the highest weight. Let pi tilde n be the irreducible representation of Su2 with highest weight n. Okay, so this is the one that looks like this. Okay, and the next weight would be n minus 2, minus n plus 2, and so on. Okay, and then we're going to check. Okay, so if we take right. So I want to figure out what pi n tilde of minus 1 is. That's what I would like to figure out. So how can I figure this out? Well, I'll use a nice little trick. I'll figure out that this matrix, first of all, I'll write it in a nice way. I'll write it as the exponential of a matrix in the Lie algebra. So this will be e to the I pi and e to the I pi. Or if you wish, I could put e to the minus I pi just for symmetry reasons. Right, e to the I pi is minus 1, and e to the minus I pi is minus 1. But I've written this now as the exponential times pi times a matrix let me write it like this. Yeah, this is fine. Exponential of the matrix I pi minus I pi. Okay, so in other words, this is e to the I pi h, because h was 1 minus 1. Okay, so the reason why this is useful is because the way that we classified the representations uses H and E and F, right? So I'm writing the matrix exactly in the format that is useful for classification of representations. So, so what do we know about this representation, right? Well, we know that you know, when we look at this diagram, this is literally telling us what H is sent to in the representation. H is sent to a matrix which is diagonal with these eigenvalues. So that means that I can immediately write what this is. This will be the exponential I pi times n, n minus 2, n minus 4, all the way down to minus n. Sorry, so now I'm writing pi n tilde of this. Okay, so when I take that 2 by 2 matrix and convert it into a big unitary matrix, the point is that the matrix that I'm testing out is literally just the exponential of H. And H, we know how H looks like in this representation. It looks diagonal with these weights. That's what these numbers are supposed to indicate, right? So this is obtained directly from the diagram which classifies the representation. Okay, and so what will this be? What will this be? Well, this is an integer. All of these are integers, and I'm taking an integer times pi I pi, right? And so if the integer is 1, if it's 0, we just get 1. If it's 1, we get minus 1, right? So depending on whether n is even or odd, we will either get minus 1s all the way down or plus 1s all the way down. So if n is even, we'll get the identity matrix. And if n is odd, then we get minus the identity. Right, 2, 0, 2, so if it's even. Okay, very good. Okay, so this means that pi n tilde descends to SO3 if and only if n is even. Okay. I just want to make sure that this argument is clear. If you have any questions about this argument, we should discuss.
Do we know this is all EREPs on SO3 because if there was another one, it would be pulled back by the adjoint to SU2. Is that right?
Yeah. So if you let's see. So yeah, if you have an irreducible representation of SO3, okay, you can pull it back to SU2. In other words, you can compose with the adjoint, and you would get another representation. You would get a representation of SU2, and the point is that one will have to be irreducible. So any irreducible representation of SO3 will determine an irreducible representation of SU2. Why is it irreducible? Well, it's because this map here is surjective. So you cannot expect to find a subspace which is fixed by everything in SU2, right? Because if you took all of those elements and mapped them here, we would get all of SO3. And there's no, and we are assuming that it's irreducible for SO3. So if it's irreducible for SO3, it's automatically irreducible for SU2. And therefore, we've already classified those. We just need to make sure which ones actually descend to SO3 and which ones don't. And the point is that it's just a parity issue. Okay, so okay, so this is a really important observation, and so it means that this is n equals 0, this is n equals 1, this is n equals 2, and so on, n equals 3. These are the irreducible representations of SU2, and it's these that descend. Okay, now I just want to say a little bit about, so notice the dimensions. Notice what the dimensions are. This is dimension 0. You could just count the number of dots. Well, sorry, this is dimension 1. This is dimension 2, count the number of dots. This is dimension 3, 4, and 5. So the dimension and the highest weight are a little bit off in terms of parity. Well, they're completely off in terms of parity. So it's the odd dimensional representations. Okay. So this means that you see, like, if we have a system, a quantum system, like a switch, a transistor, right? We know that that has it's a two-dimensional state space. And we can grab our transistor and we can rotate it in the lab. We can start rotating it by exponentiating an infinitesimal rotation, okay? And that's a two-dimensional state space, and we're doing a rotation on it. But we just proved that there is no two-dimensional irreducible representation of SO3. So this means that SO3 cannot actually act on our two-state system, okay? So it's a broken representation. It's actually a representation of SU2, not of SO3. Okay, on the other hand, if you have a chair has a vector nature. It points in a specific direction, and you can rotate a chair, and that's the three-dimensional representation. That's this one. So chairs behave under 3, okay? And there are other particles which can behave under 5. So they have a 5-dimensional state space. They have 5 classical spin states or other types of states. And SO3, we can rotate those. So the idea is that if you really want to do SO3 rotations, you can only do it in odd dimensions. That's what we've proven, okay? Now, this highest weight, these weights, so there's a discrepancy, there's an issue about the labeling of the weights of H. So what I used was H is 1 minus 1, but in physics, they always use H is 1/2 and minus 1/2. They always rescale the weights by 1/2, okay? And as a result, they would label these points in a slightly different way. In physics, I don't know what color physics is. Maybe it's brown, I guess. So this is 1/2. This is 1. In the physics way of labeling the axes. And this is 3/2, 1/2, and this is 2, 0, and 1. Okay, so they just use a scale factor, and they refer to this as spin. They refer to this group as spin. So in physics, and well, also in math, but Su2 is otherwise known as spin 3. Okay, because it is related to SO3, but it has this special, it's the double cover. It has this special nature with respect to SO3. So the way that they would call this representation is the spin 1/2 representation. They just give it that name because 1/2 is the highest weight, highest weight. And this would be spin 1, spin 0. Okay, that's just how they label the highest weight. It's literally just a labeling issue. And what did I want to say? Okay, and let me just make this a bit smaller. This is not, I'm not telling you mathematical things now. I'm just telling you some kind of social studies, the different societies. Okay, and I just want to point out that that if we have a three-dimensional space, and we put something we put an attracting force which is pointing towards the origin, and then we have a quantum particle that is orbiting this thing. Okay, so this could be like an electron and a proton. So this is a particle in a 3D central force. For example, the hydrogen atom. Okay, then there will be, from a classical point of view, you could measure the position of this particle. There would be an x1, x2, and x3 classical observables, in addition to the momenta, but I'm just ignoring the momenta for now. So these classical observables, they would become quantum observables, operators x hat 1, x hat 2, and x hat 3. And we're going to study this. We're going to study this shortly. But the point is that there is a actually, let me not talk about these observables right now. I'll discuss them later. Okay, so what's the point about this is that whatever the state of this particle is, whatever the vector space is in which that state is living, okay, what is clear is that there is an SO3 action. There's an SO3 representation on that state space, because SO3 is a symmetry group of R3 fixing the origin, right? And the force will depend on distance, and this thing preserves distance, right? So that means that we should expect that the quantum state space has an SO3 representation. So this should mean that the quantum state space, which is some big vector space, has a representation of SO3. So we should have a map from SO3 to the unitary transformations of V. And V will have some inner product. Okay, so that's just what we should expect, just because the problem is perfectly rotationally symmetric. Central force here, it means rotationally symmetric. Okay, so what does that mean? That means that the state space should be, so this, what we're going to see later is that this means that V can be written as a sum of irreducible representations of SO3, so of VI. Okay, we can decompose this into irreducible representations. And so therefore, what are we going to find? So this will be a sum of Su2 irreducible representations of integer spin, i.e. Even weight, even highest weight. So in order for the spin to be integer, we need not these, but rather these, dimension 1, 3, and 5. Okay, so this means that this particle, which is surrounding the proton, okay, its state will have a component in a subspace of dimension 1, which is trivial representation of SO3, and then it will have a vector part, which behaves the way that chairs do, in the sense that they will be modified by usual rotations. And then it will have a much more complicated 5-dimensional component, which will rotate in a bizarre way to our eyes. Okay, and these are called, this is called S, this is called P, this is called D, and the next one, number 7, is called F. This is the sharp, this is the principal. This is old-fashioned notation, but the chemists love it. Diffuse and fundamental. Okay, these are electron states around the proton. So there's going to be the sharp one, that's the lowest energy configuration, and it's perfectly symmetrical and has no features upon rotation, right? Because it's a trivial representation. It doesn't change at all under rotations. This one, the appearance of the electron will be like that of some kind of a 3-dimensional vector. So it will have a protrusion in a certain direction. And if you rotate it, it will rotate like the way that a normal thing rotates. Okay, it'll rotate in 3 dimensions. This one, however, is way more bizarre. We're going to see, I'll show you pictures and so on about it later. But when you rotate the experiment, in 3 dimensions, the configuration of electron will not rotate the way you expect. It will transform into itself and change according to some bizarre rules, because it's moving around in an internal 5-dimensional space that you cannot see. Okay, and its appearance in 3D is just that. It's an appearance, but it is not being rotated the way that you would expect. Okay, and so on and so forth. I mean, you have an infinite tower of these representations. Okay. Okay, the last thing I want to, any questions about this?
Yeah, I have a question.
Yeah.
These, like, adopting the physics convention here, like these spin half, spin 1, etc. I think I'm a bit confused onto why, like, something like the electron would behave under some spin 1 representation when, like, the electron is a spin half particle. It's a fermion. So I'm just wondering, like, is that, am I getting the spin for these representations mixed up with what we call the spin of the particles that we know, like, in physics, or am I just misunderstanding? Like,
no, it's the same thing. Of course, it's the same thing. So the point is that let me see, what's the best way to, if you throw I mean, just imagine you have a tiny little chair. If you throw the little chair, it's a particle, right? And it's rotating and everything. That thing is behaving like a vector. Okay, so spin is about when I rotate my lab, right? All the properties of that thing, how do they behave? Do they behave like a vector in R3, so that when you rotate, it behaves like this, right? You could write a 3x3 matrix, you rotate by a certain angle, and then you get a sine cos matrix, right? That's what a spin 1 particle is. That little chair is literally spin 1. Okay. The discovery of the main discovery that they made of electrons, about electrons, is that they're not spin 1, that they have something else. Like, they thought originally that there was only spin 1, spin 0, spin 2, like that. Those are the normal representations of SO3. I mean, maybe it takes you a while to figure out that there's a 5-dimensional representation. Okay, but it's not that difficult, because you could, well, okay, there's ways of building representations, like by taking tensor products, right? And you could easily discover that not all representations of SO3 are of dimension 3. I mean, once you see that there's a dimension 1 and a dimension 3, okay, maybe it would take you a while to discover this. But the really incredible discovery was, and this is why they had to call it 1/2, is because they're like, uh-oh, we kind of totally missed a whole bunch of representations that are in between the obvious ones. And so this is spin 1/2. So it's like the electron is behaving completely wrong. It's not behaving the way we expect, because when I rotate the lab by 360 degrees, my state is going to negative itself. And they're like, what the hell is that? That's obviously not a spin 1 representation of SO3. So they had to figure out what that is. And they realized that the problem is that SO3 is not simply connected. It has a double cover, which is non-trivial. And that's the group that you're really using. That's the real symmetry group of nature. So when you start doing your rotation, you're exponentiating a Lie algebra element, but you don't know which Lie group it is, because SO3 and SU2, they have the same Lie algebra. So you are infinitesimally doing things, because you're so small and slow, or whatever you want to call it, right? You're just following a path, following your nose. You don't know what the global structure of the symmetry group is, right? And what they realized is that the global symmetry group is SU2, and that there's a whole bunch of representations in between the obvious ones. And that's what the spin of the, I guess you could say, the angular momentum of the electron is not a vector in 3-dimensional space, like the angular momentum of that chair. Sorry, I should have said that. If you take that chair and spin it, right, it will have an angular momentum which is described by a vector, by the right-hand rule. Okay. So the point that the thing that they really discovered is that the electron has an angular momentum, but that angular momentum is not a vector in 3-dimensional space. It is a half spin type of vector. Okay. And so if you rotate, like, that's the point. So I hope that makes it more clear, is that every particle will have an angular momentum. Every object will have an angular momentum. And that angular momentum is a state. And it will be affected, that state, that vector in some vector space, that will be affected when I rotate the lab. Okay. And the rotation of the lab, in truth, when they tell you the truth, is really SU2, not SO3. So the point is that SU2 is like a global symmetry of nature. It's like part of the Lorentz group, right? And it will act on all state spaces of all particles of everything. It will act on everything, including the angular momentum. The angular momentum is a vector in some kind of vector space, but they're not all 3-dimensional vector space. There could be a 2-dimensional vector space, a 5, anything. It could be any dimension. And you have to figure out, for any given object, doesn't have to be an elementary particle, it could be an atom, could be a half of an atom, could be only the nucleus, it could be a person, whatever. They will have an angular momentum vector in a representation of SU2, and you need to determine what it is. Most people, like myself, they're not irreducible. I'm made up of a bunch of different particles, right? And it's not irreducible. So when you go down to when you keep splitting and splitting and splitting, you end up to what we call elementary particles, which are basically just the things that are irreducible under the symmetries of nature. So this is what we're seeing with this. I don't know. Does that That should make it
Yeah.
crystal clear.
Yeah.
hopefully.
So I think then my confusion is like if the hydrogen atom, which has one electron, that this central force quantum system, like why would decompose into only integer spin representations when it just can describe half integer spin?
Okay, thank you. Very good. Okay, so that's a very good question. So, like I said, when you rotate the lab, okay, when you rotate the world, every possible state space, every state space is affected by that. Everything is a representation of the SU2. Okay, not just the angular momentum state. It's also the position state. So this electron that's rotating around the atom, okay, it has a position state. Okay, and it has an angular momentum state. It has an angular momentum state with respect to the origin. That's quite apart from its intrinsic angular momentum, which is a separate thing. That's a different state space. So the electron itself is a spin 1/2 particle, and it has a spin state, okay, which is, you could think of it as an angular momentum state, it is, but it has a spin state, which is a 2-dimensional state space, and that you could think of that vector space as being hidden deep within the electron. But this electron is moving around this atom. So let's forget about its internal spin state, which is a tiny, tiny amount of momentum. Anyway, who cares about it? The main amount of angular momentum is that electron moving around the proton, okay? And that has a much bigger angular momentum, which is a vector in a vector space. And the cool thing is that it's not a 3-dimensional vector, that thing. Part of it is the P, the principal component of its angular momentum, or a so-called orbital angular momentum, okay, is in, well, anyway, we're going to discuss this. We're going to discuss this in greater detail. I just don't want to get too confused. The point is that in truth, you have to take a tensor product of the internal spin 1/2 representation with all of these. All of these things that I'm talking about for the hydrogen atom, they have nothing to do with spin. That's why they always say, we're going to teach you these SPD orbitals, but actually we have to tensor by a 2-dimensional space. So there's always 2 electrons in each one.
Yeah, okay, that makes sense.
Up
Like,
and
we're
down.
not even trying to describe the internal intrinsic.
We're not trying to describe the spin 1/2 particle. We're
Okay.
trying to describe any particle. There is no internal dynamics of this particle. This particle is just, it could be anything. It's just a point particle with no internal structure, but it is moving around a point in 3-dimensional space, and it will have a state space, a quantum state space that is a representation of SU2. So it doesn't even have to be an electron. It could be literally a planet moving around the sun. I mean, it's honestly, it's not, yeah.
Okay, that makes sense. Thank you.
You're welcome. So the last thing, I'm already over time. Okay, I better stop. Okay, I'll see you on Friday. There's office hours now. I'll leave it there.